Great. Welcome, everyone. My name is Megan Carter. I'm ESIP's Community Director, and I have the pleasure of supporting this session today. I'm going to turn it over to the session leads in just a moment, but I wanted to remind you that this session is being recorded. As you already know, we're using Zoom as our platform. In case you're less familiar with Zoom, I don't know who is at these days, but at the bottom of the screen, you see a number of options. You can open the chat window, you can click and open the participant list. We have a couple of general guidelines. Please mute when you're not speaking. Cameras on during discussion, maybe off when the presenter is presenting. Oh, and I realized there's a funny effect going on here. You can switch between gallery and speaker view. If you have any questions about the technical features of Zoom, feel free to send me a message. More importantly, I wanted to remind you about the ESIP community participation guidelines. The guidelines, which are similar to a code of conduct, are meant to outline expected behaviors and behaviors that will not be tolerated in the ESIP community, as well as what you can do if you believe you're experiencing unacceptable behavior. There is a link that I will pop into the chat box with more information about that, and know that there are anonymous ways to make a report if you so choose. So with that, I would like to hand it over, I believe, to Matt Hansen.
Yes, hi everyone, and welcome to the session on STAC. We are going to have 4 talks today. I'm going to be actually giving a real high-level sort of overview of the state of STAC. Scott Henderson will be showing how to use CMR STAC, which I'm going to mention in my talk. And then we have Rob Emanuel from Microsoft, who's going to be talking about all the cool things that they're using STAC for with their Earthon AI. And finally, Vincent Sarago from Development Seed is going to be talking about his awesome dynamic tiling work. At the end of each talk, we're going to do a little exercise where we all take 1 minute. We'll time it, where you can type in your takeaway, your thoughts, 1 sentence on each of the talks into the chat, and don't hit enter. We'll do a minute. That way you can't read what anybody else has written. So you'll take a minute, and at the end of the minute, you all hit enter, and then we have a bunch of information that we can put into Slido and create takeaways for the overall session later. So without any further ado, I'm going to jump into my talk. Okay, can everybody see this? Okay, I got a thumbs up. All right. So the state of STAC. If you've seen my previous talks, I generally talk about STAC and how why we needed it, what it's useful for, what it looks like. And this today is going to be more of a news update on exactly where things stand today on 3 different aspects of STAC. One is the actual specifications themselves. The other is on the open source ecosystem that's available. And then finally on actual STAC data that is available as public catalogs. So the STAC spec. So here's just a little example to review in case you actually are kind of somewhat new to STAC. STAC is primarily JSON. Items are GeoJSON. Here we have a Landsat, example Landsat item. It contains the geometry, which is the footprint. We have a variety of properties. You'll see that there are some prefixes there with colons. Those are something that's called extensions. So there's core fields, there's extension fields, and then we have assets that actually point to underlying files. So this item can represent, it represents a single scene. So that's a single location for a certain date time. But there can be a variety of different file assets, multiple file assets. In this case, it's one for every band, plus some additional ancillary data. So the STAC spec is actually 2 different specifications. This is actually in itself a relatively new development. When we came up with STAC 1.0 beta, we split the API spec into another repository so that we can version them separately. So the STAC spec itself, this is the specification that talks about the metadata, what things are called, the static structure of that. That's on 1.0 beta 2, and it's been since July. We're probably planning on coming out with a release candidate version quite soon. The STAC API spec is the specification for the actual RESTful API that is based on OGC API features. And this is one reason why we split this out into a different specification, is because it's really extensions on top of this OGC API. It didn't make sense to loop it up into the STAC spec. So we have a variety of content extensions today. You'll see this is a list. There's actually several that are in PR phase. Again, off to the left, you'll see this an example of using prefixes. Here we have an EO, the EO extension, and the view extension is being used in this example, but there's also L8, which is a vendor extension. So if you're using STAC yourself, you could always have vendor extensions as well for additional fields that you might want to add. But the extensions listed here are the ones that are currently included in the repository on GitHub. There's quite a few there, so I'd just like to point out the key ones. Actually, let me go back. So you'll see the maturity level there. You'll see that they're all actually in proposal stage, and that's just because we haven't actually gotten around to incrementing the maturity based on usage. So the idea is that there's different maturity levels for extensions based on how many implementations there are out there. And so the ones that I have sort of identified as the most common and the most widely used are these ones here. The EO is probably most common because it's used in Landsat and Sentinel-2, which are our two largest catalogs of STAC data currently available out there. And this allows information on spectral bands and cloud cover. SAR also has been used quite a bit. The projection extension it allows information on the geotransform for assets, and that's actually proven to be very useful because if you're familiar with Open Data Cube uses this information to actually index data without having to hit the individual files. All of the information there is included right within the STAC file, which is pretty cool. The satellite and view geometry extensions contain additional information on the collects. And the single file stack is sort of unusual in this list because it's not really a content extension like the rest of these are. The rest of these actually add fields. The single file stack extension is just a way to, it's essentially a GeoJSON feature collection. And then you can also put stack collections in there. So you have a complete catalog in one file. Because if you're familiar with STAC, you know that it's a series of linked files. But if you, for instance, do a search and you end up with several hundred files, maybe you just want to actually put those into one feature collection because you can open that in something like QGIS and look at all the footprints, for instance. So, and it's more portable that way when it's a single file. So likely changes before we get to a 1.0, like you know, what's going to happen between now and then? Can we expect some major differences? And the answer is not really. We've added some additional rel types for data provenance purposes, lots of clarifications, wordsmithing, best practices has been a big push. Like, you know, it's actually not part of the spec that you have to do this, but what are the best practices? How should we do this? How should we organize our data? Lots of fixes to the JSON schemas, really trying to get those solid. Some minor changes to some extension fields, nothing in the core, but some extensions might have a field name changed. We're currently right now discussing adding the STAC type field. There seems to be a lot of interest in doing that. I think that's probably going to end up happening so that there's an explicit field that says what kind of STAC entity this is, a catalog, a collection, or an item. And finally, there's a variety of new extensions that are probably going to be pulled in before 1.0. The processing and file info extension are already in there since the last release. And of particular interest are a couple card4L extensions. If you're familiar with card4L, it's a specification, sort of best practices really by CIOS to describe analysis-ready data. So now the STAC API portion. So STAC API is extensions built on top of OGC API features, as I mentioned before. So you see a list of these features endpoints here, and then I've circled some of the search endpoints. Down in the lower left, we have STAC endpoints. STAC essentially adds these endpoints to OGC API. And these are all described with open API documents. Just like extensions to the regular STAC spec repo, we have API extensions as well, which aren't content extensions. They don't add metadata fields, but they add behavior and features to the API itself. For instance, the sort extension allows you to sort. These are typically going to be extensions that if you provide search, a lot of these you're probably going to end up implementing as well, especially the query extension and the sort extension would really be among the most common because you want people to be able to query on arbitrary parameters, which is what the query extension here does. The transaction extension allows you to actually add data. So here's the query extension. I'm going to not really spend any time on this because it's going to get replaced, but here we can sort by any field. We can query on any property field. So you could say anything less than 10% cloud cover and then sort that in descending order, for instance, by date. One of the big pushes recently that we did before we released the 1.0 beta 1 version of the API was really get the conformance classes set up and solid. So these conformance classes are basically a way for the server to advertise what its capabilities are. You're probably familiar with this with other RESTful APIs. OGC API features has its conformance classes. STAC adds some conformance classes for each of its endpoints, and then each extension has also a conformance class. So when you go to the landing page, you'll see the list of what capabilities this API actually supports. So that's been really quite important, maybe not for most users, but to really make sure this is stable going forward and can be, machines can understand what the capabilities are of a server. So likely changes before the STAC API spec comes out. This is a little bit more nebulous because there's going to be changes to the OGC API features standard, which we will align to. And I mentioned we're getting rid of the query extension. OGC API is adding something called CQL for doing more complex querying, and that's probably going to be the main query language that STAC API uses. So whether or not the query extension is deprecated and CQL added at version 1, or we remove it completely, that's still to be determined. But that's probably the largest change that we're talking about. And that would require some changes to various clients. So now the question some people might be asking is, when does a 1.0 come out? I don't know, maybe this year. Really, the main driver is looking for more catalog implementations. I suspect the RC1 for STAC spec will come out in the next couple months. STAC API, depending on that OGC API. One important thing to note here is the recent announcement discussion about how STAC is going to become part of the OGC, the organization, as a community standard. So maintenance after a version 1, this will really be handled within OGC. So now we've got the open source ecosystem. This is not all of the software that's out there. This is really the software that either I've been involved with or I'm just familiar with. I left out one really important one that Scott Henderson's actually going to be talking about. So that's why I didn't have it in here. But for developers, when you're starting off, one thing that you might be really interested in is validation. And so there's a STAC node validator. There's also a STAClint website that you can use to just drop in like a single item and validate if you're playing around with creating your own stack, that can be pretty helpful. Pi Stack is really a foundational, really important foundational library in all of this. It's a Python library. It's for working with stack files. I say it's for developers because it's probably one of those libraries that would be a dependency if you write some other library that's going to use Stack. You can read and write Stack with it. It does validation. It's got support for most extensions. Really, if you're doing anything in Stack and you use Python, this is the library to go to. Finally, we have, for the developer side, we have servers. So there's several different server implementations out there. So with Stack, you have static files. And if you want them to be searchable, you need to read those and index them somehow. And so that's what these servers would do. There's several different ones. The one that we use at Element 84 for Earth Search, which I'll mention later, is Stack Server. But there are some others in variety of different states. I think most of them are generally compatible with the latest version. Well, with 0.9, I don't think they take into account all the changes with the conformance classes. So for users, we have Stat Search. Stat Search is an older library. It's been around for a little while. There's probably going to be something to replace it at some point based on Pi Stack, but for right now, this works really well. You can easily just install, and there's a command line for just, you have a GeoJSON, you can search the API and get a bunch of results and download those. Really quite helpful. If you're an end user, this is one of the, and you like command line tools, that's what I would use. Stack Tools is a high level CLI and library. That's higher level than Pi Stack. It's based on Pi Stack, but it's really aimed at adding in the ability to create stack from raw metadata. So there's various sub packages for generating stack from Aster data or from Landsat data, soon Sentinel data. And so that's what Stack Tools is for. Or I want to create a stack from a GDAL file. Like, these are the types of things that we anticipate that Stack Tools would be used for. Stack Browser is a way to browse and look through static stack sites. I'll mention that again later. I'm probably running out of time here. And then
you're at 14 and a half.
Browser, what's that?
You're at 14 and a half.
Okay, all right. I'm gonna go over a little bit, but
okay, that's okay.
So Stat API Browser is really a prototype that Development Seed had done a little while ago, but the idea is that you can point this at any Stack endpoint and be able to search it with a pretty simple API. So that's pretty nice. And then Rocket is a great demo if you want to check that out. Snap Planet Rocket. You can actually put in any API into this interface and use it. And there's a nice Stack demo catalog if you go to that page that has Landsat and Sentinel on it. That's pretty cool. Okay, briefly, I just want to talk about pipelines because this is a new sort of type of software for Stack, stack-based pipelines. There's been a lot of talk about this. We've done stuff at Element 84 on this. I think there's a lot of potential here. I think we're going to be seeing more of this idea that Stack is the metadata that can go through pipeline. See a little diagram off to the right. Each of those is a step through this pipeline, and you can think of it that every step takes in Stack and an output Stack. So you get to like a add preview step, you have your Stack input, and that step takes some of the assets, creates a preview, and adds that as an asset and spits it out. So your Stack item is growing as it goes through, or maybe moving to different places. You can move it and then those URLs are updated. So being able to chain together workflows and track that data provenance back to the beginning, I think there's a lot of real great possibilities here. Here we see an example of how we can track that data provenance in the links of any particular item. So we have something at Element 84 called Cirrus. It's open source. It's based on AWS, mostly serverless, and it's written in Python. I don't have the link here, but there's an org called Cirrus Geo. Digital Supercluster is something that Canada has funded, and SparkGeo and Earthcast have been involved with, and it's really, there's a lot of similarities there. They're approaching this with the idea that STAC is a messaging protocol through a pipeline. And then CMR STAC, oh, I think I missed one. Okay, public STAC data is the last section. So there's a few different STAC catalogs out there. There's STAC CMR here. Scott's going to be talking about that, so I'm not going to spend any more time on it, but it's a proxy to NASA's CMR repository that's all in STAC, that's STAC compatible. At Element, we have Earth-Search, which the idea is that this is an API for various AWS public data sets, although currently it's several different Sentinel products, both the level 1C and the level 2A products in Europe, and plus the COGS that we have generated. I'm happy to talk about that offline for anybody who wants to know more about that. And then finally, if you don't know, if you don't take away another slide from this entire presentation, this is the one to go to, STAC Index. STAC Index is a great new website. I didn't list all the data sets. STAC Index, the idea is that you go there and you can have a STAC browser. It automatically adds a STAC browser to any STAC catalog that's been added to it. It's got a collection of all the software that's available. Really, this is a one, if you're new to STAC, this is probably first place that you might want to check out in addition to the STAC Spec website. That's it. Thank you. Sorry for going over. I guess let's do our minute now. So if everybody could just type into the chat and don't hit enter, we're going to start now.
And just a reminder, Matt, so this is to write a takeaway?
Yeah, takeaway, like, some thought that you have, sentence or two or something. And I see that there's a question here in the chat, but we'll do questions at the end. All right, so that's just about a minute. So if everybody hits enter, and then there's a whole bunch of new messages there in the chat, so that's great. So thanks for doing that. So next up we have, actually, who's supposed to be next? Is it Rob or is it?
You want to take some questions now, Matt, or do you want to wait until the end, or how do you want to do that?
Well, we could do it. I mean, I just see one question here, really. So from Alan, yeah, maybe we should just answer this one now since it might get lost. So Alan asks, does it make sense to include extensions into STAC versions versus each extension being maintained separately, but tied back to which STAC versions? I do think that makes sense. We have had that discussion within the community about whether or not extensions go in that core repo or not. And I think that this ties back to that maturity level. I think that we'll find that what we'll do is some extensions might just be part of core because they're commonly used. And then other to be determined, really, I think. But what you say, I think, makes a lot of sense. Some extensions might be versioned separately and in separate repositories.
Matt, there's also a question from Dave Neufeld about, how to handle other commonly used collections of metadata. Oh, Dave, go ahead.
Oh, yeah, just suggesting a little bit of collaboration on property attributes. And so, yeah, it was part question, part statement. And maybe we should come together on like an ESIP vendor extension to manage those properties and just kind of follow a lot of community standards that are already sort of in place. Just so we're not kind of trying to rethink what those property names are or looking, at different names across different vendors for things that content-wise are basically the same.
Yeah. Yeah, no, I think that's a great idea. I mean, we always try to use existing, looking at other existing standards when coming up with these things. And I think the Card for All extension coming up is a good example of taking what they have done and trying to put it in there, not trying to reinvent the wheel. So I think that's an excellent point. Okay, and I think maybe we should move on here because I want to make sure everybody has plenty of time. So who's supposed to be next? Is it Scott or is it Rob?
I believe I'm next on the schedule.
Okay, great. Rob from Microsoft, take it away.
Very cool. Okay, let me share my screen and press the button.
So do you want me to give you a 5-minute warning or anything?
Yeah, if you could, I don't know the best way to do that if something flashes up in 2 minutes, but I'll just try to be relatively on time.
All right.
Cool. So hi everyone. My name's Rob Emanuel. I'm with Microsoft's AI for Earth, and I want to talk about how we're planning on leveraging STAC. So as context, I just want to talk about environmental sustainability at Microsoft and why we're dealing with this type of data. We have an environmental sustainability team that's focused on harnessing the power of technology to help everyone everywhere build a more sustainable future, right? And so we last year made pretty specific commitments around sustainability in 4 focus areas: carbon, wastewater, and ecosystems. For carbon, we made a commitment to be carbon negative by 2030, and not only that, to be by 2050 to remove all the carbon that's ever been emitted since the foundation of the company, and that is including like upstream and downstream with the vendors that we work with. We committed to be water positive by 2030, meaning we'll replenish more water than we consume on a global basis. Committing to zero waste. So by 2030, we'll divert at least 90% of our solid waste headed to landfills, manufacture 100% recyclable surface devices, and a number of other very specific commitments. And then so for ecosystems, we have committed to, by 2025, protecting more land than we use, and also building and deploying what we're calling a planetary computer through our AI for Earth program. And I'll touch on that later, but I want to talk about AI for Earth as a program. This is the team that I'm a part of. The program's aimed at the ability to monitor, model, and ultimately manage Earth's natural systems. And we see ourselves as sitting between environmental science and computer science, trying to bring technology that Microsoft can provide to these efforts. And the program has 3 pillars, right? We're a grants program. So we give grants to organizations doing sustainability work through cloud credits or more direct funding models. We're also an open data program hosting key environmental and conservation data sets. And we're building tools, services, and infrastructure to accelerate the work of environmental sustainability. So our grants program is wide. We've been around since 2017, and we have over 700 grantees worldwide who we're supporting. And since that inception in 2017, we've been building technologies not necessarily geospatial focused. For instance, we have a camera trap service that uses machine learning models to classify species in camera traps for a wide variety of organizations. This is a really cool part of my job. I'm used to looking at satellite imagery, which is really awesome, but now I also get to look at pictures of animals in the wild. But I joined the group 3 months ago, specifically because they're building an engineering team to build out what we're calling a planetary computer, right? And this is a pretty grandiose term, admittedly, but I think the vision is large, right? It's what are the ways that we can use Earth science data to derive information about the Earth and put it at the fingertips of people pushing forward environmental sustainability. And I'll quote our chief environmental officer saying, "Sure, it's an ambitious idea, but its promise is unprecedented." And I believe that long-term vision is true, but we certainly want to walk before we run. So our near-term focus is building out foundational building blocks around data, access to that data, analytics on top of that data, and applications using that technology. So like other cloud providers, we're hosting open data sets on Azure. We're pretty far behind in the sort of open data game, but we're catching up, building ETL pipelines to onboard new data sets as we speak. And I like to make the point that just because data is available doesn't necessarily mean it's accessible. If you host data that's accessible through a HTTP endpoint, that's great. But it's not enough to say that it's accessible. It's only available, and this is really where STAC comes in for us by providing metadata that lets us classify the data in a machine-readable way that allows things like STAC APIs to be built on top of them and allow users to do spatiotemporal queries to find the pixels that they really need. We're enabling access. And this is sort of a differentiator for us, where we're not just hosting data, we're providing and maintaining services to directly to enable access. We're doing that through hosted services, generating STAC metadata, hosting STAC APIs, and also providing some data access APIs through OGC standards like OGC API tiles, and then supporting open tooling around accessing our data through those mechanisms. We talked about, or Matt talked about the ability to search STAC endpoints. That's something that I see us really supporting in the ecosystem. We're really focused on analytics and compute, right? So once you have access to data, you need to do stuff with it. And there's other platforms out there for doing really awesome analytics on earth science data. We're taking an open architecture approach and really trying to leverage the amazing tooling that exists out there in the open source community and enable it to run in our environment. So that includes a hosted Jupyter Hub instance that is, has a DAS cluster that you can spin up CPU and GPU instances on. But also, if users want to use the data directly, or if they want to, bring their own compute, we want to enable those use cases as well. And so my colleague Tom Augsburger, sorry, let me just make sure this video is playing. There you go. My colleague Tom sent me this, screenshot or a video of him processing some of our data. So this shows loading daymet data stored as ZAR files on Azure Blob Storage into an X-ray data set, averaging low temperature over the decade in North America. And this is showing as new workers are added, there's a cluster map where the colored lines indicate tasks being assigned to the from the scheduler to the workers, and then red lines between workers is moving data. It hasn't really spun up yet, so you'll see that in a second. And this is just an example of these are tools that exist in the ecosystem that we want to leverage and support as part of our analytics platform. And then on the other side, there we go. We want to support data science in scientists using our platform, but also applications that use the data directly to people to serve information to people doing direct impact work. So somebody's off of mute. If they could just mute themselves, is a little distracting. Thanks.
Pardon me, sorry.
Yeah, so this is an example of an application that we supported through our AI for Earth Grants program and Signature Project, where the Freshwater Trust and upstream tech work together to build a platform to help identify the best places to improve groundwater and surface water quantity and quality. So this isn't using the planetary computer infrastructure yet, but is the type of application we want to support. The type of workflow that we want to support. It's pretty common. We have a lot of land use land cover work going on at Microsoft. And so just an example, planetary computer workflow would be, asking a question like, how do we apply land use land cover models at scale against Sentinel-2 imagery? And really a general workflow would be query Sentinel-2 images over date range and AOI, and then bring that into a DAS cluster, do some work to co-register images, mosaic via mean, right, to get rid of some clouds, and then use your PyTorch or whatever model you develop to run inference on the tiles. And this is where we see, we're not trying to build proprietary or custom components to do this work. This is just stringing together the amazing work that's happening out into the open. Out in the open. So to talk a little bit about some of the tools we're using or planning to use, this is great, Matt. Thanks for already covering this stuff. We're using PyStack. We're a Python group, so really leveraging PyStack for the core foundational library, and then STAC tools, where we have ETL pipelines for bringing in new open data sets and running on our infrastructure to extract metadata and convert to cloud optimized formats. And then so the first step of that is to contribute to STAC tools, the data set we're working with, because we want, really, I see a vision for STAC tools to be a common ground where we can all be using the same logic to extract metadata and convert things to cloud optimized format, because users shouldn't have to worry about which vendor their data is coming from and the different interpretations that different vendors are supplying for the STAC metadata. It should be consistent and it should be correct, and we should all be collaborating to make sure that it's correct. So we want to be able to participate in that and contribute to STAC tools for the metadata that we're deriving. And I invite people to also do the same for any data sets that they're working for conversions on. For our
5 minutes, Rob.
5 minutes?
Yep.
Cool. So for our STAC API, we're working with the Arturo STAC API. We really like the design philosophy of this fast API, making sort of thin, composable Python routes. So working with Arturo and the maintainer of that project to make it more community driven and support that. And we're also, for our data API, are using T-Tyler, which Vincent will be talking about later, which is a very awesome project. So yeah, we're going to be looking to help collaborate with y'all to build out the STAC ecosystem. And we have tooling that Matt went over in sort of all these 4 areas. And I think that there's a lot of opportunity to mature those tools. So, the generation and validation tools, we have STAC tools and PyStack, the STAC API server, like Matt mentioned, there's a range of them. We're looking to get the Arturo STAC API base to sort of be a canonical exact spec version for that. Client-side search, what are the tools available to people to actually have access to this data once it's in hosted APIs? And then, yeah, visualization, STAC browser, which STAC Index is using to explore STAC data sets, is a great start. And I think that there's a lot of work that we can do to enable sort of front ends to be able to visualize and search STAC endpoints. And so I want to call out this repository in the STAC Utils organization. Chris Holmes, really appreciate his leadership in the STAC ecosystem. He put together a document that sort of outlines some thoughts around what are the different tiers of maturity that we'd like to see in the STAC ecosystem. And we'll definitely be looking to this and collaborating with this to try to mature out this ecosystem of tooling. And I invite everybody to collaborate. Put your ideas in. If STAC does not fit to the data set that you're working with, raise a voice and let's make sure that it does cover your use cases. And I'll just end with a note that, yeah, AI for Earth is looking to work together with technology and earth science communities we're a small team, but we have a pretty incredible opportunity to like strategically invest in these open communities and open data communities, open science communities, and partner with organizations to try to maximize our impact. So if you're doing work in this area, if you have ideas on ways the planetary computer effort can push things forward, please reach out to me or reach out to planetarycomputer@microsoft.com. Thanks.
Thanks, Rob. Very cool stuff. We talked about this the other day, and to me, it seems like using Pangeo for within this ecosystem here. It really seems like Microsoft is building an open version of Google Earth Engine. Where Google Earth Engine is a black box, but this is going to provide a lot of the same capabilities. So I'm super excited about this. It's great. Glad to see. I have to point out though, like planetary computer, that term is actually pretty awesome, because I don't know if this was the thought behind it when whoever came up with that, but in Hitchhiker's Guide to the Galaxy, the Earth is a computer to answer the question of life, the universe, and everything. They build Earth, and it's supposed to be a computer, and then of course it's blown up by the Vogons right before it comes up with the answer. But anyway.
Yeah, that's awesome.
You'll have to ask about that.
Yeah. I know Satya Nadella, the CEO, talks about building Azure as the world's computer, and then the chief environmental officer talks about how that computer is often just used to process information about ourselves and consumer behavior and targeting ads. And it's what we really need to do is shift all of that infrastructure, or at least make room for that infrastructure to talk about our planet and taking the pulse of the Earth. So I like that. I like that analogy of the Earth is actually a planetary computer itself.
That's right. Yeah. All right. So why don't we take a minute? We're going to start now and write in a sentence or two, takeaways about this, and then now there's a bunch of chatter about Hitchhiker's Guide to the Galaxy. So I was successful in that.
And my Telecaster. Good way to point it out.
Yes, that is awesome. Well done.
Seeing your sweatshirt there, I feel like I missed an opportunity to wear my STAC sweatshirt or a STAC shirt or something. So Rob's gonna probably go get his. Oh yeah, nice.
I still think it might be the first time I've ever seen Matt in a shirt with buttons. This is a first.
Yeah, well, at least I didn't.
I was gonna say something, but I didn't.
Okay, so a minute's up. So everybody hit enter, and okay, so thanks again, Rob. So next up, well, actually, is there some questions here? I don't know if I see any questions. I might have gotten lost. So at the end, if there was any question, you can.
I see one. Is there a project roadmap for these pieces, such as STAC API for public data sets on Azure? Our plan is to roll out that with a set number of data sets in the spring. So look for that, and then we'll have sort of quarterly releases that add additional data sets and additional functionality after that. But we're still in the building phase. If you're more interested in talking about what specifically we're planning, please reach out. We'll be happy to share.
Okay. So let's see. So Scott is up next, I believe. So Scott Henderson is going to be talking about CMR stack and use of an intake stack, which I didn't mention. So
That's all right.
I mentioned it, but I didn't talk about it. So all right.
Let's talk about it. So, cool. Thanks, Matt. Can everyone see my screen here? See a nod. Thanks, Amy.
Yes.
So, all right. Today I'm going to talk about a library built on top of STAC. It's called Intake Stack. I'm a research scientist. I work at the University of Washington, the Department of Earth and Space Sciences, and the eScience Institute, which is a data science institute on campus. So this is very user-focused kind of presentation of how we might use STAC, and specifically how we might integrate some tooling, Python tooling, with NASA's archive. So if you want, you can go to this link. I should have said the slides are linked both in the Kiko chat, Google Doc, and also on the ESIP Fed schedule. And there will be various links throughout these slides. The goal was just to get people familiar with kind of the big picture. But if you want to dive in and run some interactive examples, if you're tired of Zoom, you can go to this repository here on GitHub for Intake STAC, and there's a launch binder button to run some interactive code examples in a notebook. This is a pretty new library, so there's some documentation here on making contributions too, which would be great. So what is this project? The Intake STAC, as I mentioned, is a Python library, and it came out of some work funded by the NASA Access program in 2017 to develop community tools for analysis of NASA Earth data observation system on the cloud. So we heard a little bit about the Pangeo project in the last talk. Rob pointed out that this is a nice kind of ecosystem of open source tools for large scale computing. And this is really important for working with NASA imagery as the archive grows to petabyte scales. It already is there, hundreds of petabytes, let's say, in the coming years, and is beginning to be hosted on cloud services. So this project was recognizing this transition and building out tooling to enable researchers to more effectively work with NASA data sets and ultimately just accelerate scientific discoveries with this data. So traditionally, probably still today, I'd argue that a lot of folks are accustomed to working with NASA data by going directly to a specific NASA distributed archive center or DAC. So this is great because we have domain specific places to get access to data sets. But each of these distributed archive centers often have a different API that you have to learn if you want a specific data set there. This kind of model of searching and getting links and then downloading those links to a computer is also restrictive because you have a bottleneck for downloading as these files become larger. And it's also quite difficult to share your work with collaborators because you end up duplicating a lot of data and need to have it locally. So there's a lot of promise in this move to cloud hosting, cloud architectures, whether it's on Azure or Amazon Web Services or some other public cloud service. But the vision here is that you move your scripts and algorithms onto a service into that data center where the data is stored and take advantage of some of the promises of cloud computing in terms of elastic scaling of compute. And also it will hopefully increase access because people are going into the same system. It therefore becomes easier to share your analysis rather than having to share the data itself. But this is like the grand vision that isn't necessarily fully achieved yet. And you'll notice in our diagram on the slides here, where we have everything encapsulated in the cloud, one key component of this workflow is data discovery. Once you know where the data is that you're working with, and this is to Rob's point of data being available isn't accessible, it needs to be accessible in that system. And we sort of recognized early on that STAC was a key way to enable that accessibility. And this slide is borrowed from Shel Gentman's presentation at the ESIP summer meeting and sort of frames the idea behind Intake STAC, which is we need a few kind of small libraries to fill in gaps to make it easier for scientists working with data to spend more time interpreting and less time with the downloading, cleaning, etc. So how does this system work, Intake Stack? Well, a few years back, and this has probably changed somewhat, we put together a table of current cloud-hosted data sets in AWS, and we were just noticing a lot of different formats, often no accompanying metadata to these files, just object store with links that you had to construct yourself in order to get to, for example, imagery covering a specific bounding box and time. And as Matt pointed out, STAC really addresses this issue by providing lightweight metadata that really emphasizes kind of user-facing search and ease of construction and discoverability of remote sensing data specifically. So with any one of these data sets, whether it's NASA or another provider, providing this STAC metadata along with the assets themselves, so the images, is key for discoverability, because then we have information about geospatially where each file sits. It's much more accessible. So the design behind this Intake Stack library was to create a lightweight Python package that allows researchers to easily load remote data into their computing session. And so this is Python focused because Intake is a Python package. STAC is just simply JSON metadata format. So it doesn't matter what computing language you're using there, but this library is specific to Python. And the goal was to use an existing tool, an established tool, Intake, which really facilitates data management and input-output on files into Xarray data objects in Python. So Xarray is another Python package specifically designed for working with multidimensional data, which we often have with imagery. We often have multi-band imagery or temporal stacks of images. And our goal here was to, if given an intake catalog, can we very easily load this data into Xarray? And it turns out you can quite easily, because STAC provides a description of not only where the file sits, but also a MIME type about the description of the format that data is. And so given those two things, you know how to open up a file and bring it into the Xarray library. So most of the time we start with a search. If STAC catalog exists and is indexed with a tool like Earthsearch that Matt talked about in his presentation, we don't have to construct URLs, right? We can use a standard search with standard metadata fields and get back a list of items, which would be acquisitions of a satellite, for example. So this example here is searching Sentinel-2 data hosted on AWS. Once we've loaded a catalog into the intake system, the goal is, once again, to bring it into Xarray. And we can do this by looking at item IDs rather than file paths. So Matt mentioned this is one of the required fields in a STAC catalog is an ID descriptor. And Intake provides different drivers given what the file type is. So you'll notice in the code example here, we're not specifying what type of file this Sentinel-2 image is. We're just selecting a band and loading it into Xarray via a toDask function. So as a user, you're really not concerned about the data format. Most users aren't interested in that information, just really want to write a script that brings the data into their session for an analysis. So Intake Stack is sort of providing this abstraction between the underneath data and then getting it into your analysis script. So the data format could change in the future. Maybe today we have a netCDF file behind the scenes. It could be a cloud optimized geotiff. It could be a ZAR format, etc. And depending on that format, this performance can be quite good. If it is a cloud optimized geotiff like Sentinel-2, we can load it into an Xarray object just by reading the metadata. So we're not reading the entire file. And that is key for quick performance and then enabling distributed computing as these data sets grow in size. So once we have an object referenced by Xarray, Xarray becomes the API for common user interactions such as subsetting or reprojection, and really any computation you might want to perform if you have code set up to run computations on, excuse me, NumPy arrays, for example, in Python. And we're sort of building up and developing this library with the ultimate vision of making it very easy to work with larger and larger stacks of imagery. So temporal stacks, for example, where we might want to look at all Sentinel-2 images or Sentinel-1 radar, is the case I'm showing here, over specific points in the continental US, and extracting time series, for example, from cubes of data. So finally, to get to how this integrates with NASA data sets, NASA has the common metadata repository, which folks on the call may or may not be familiar with. Essentially, it's an effort to consolidate these different APIs and hosting services at individual NASA archive centers in a single interface. So this is what backs the Earth data search, where you can go to search for any NASA data sets. It's a metadata and search system. There's a relatively new effort to put together a STAC proxy for this CMR search. So what this does, and there's a link to the repository here on the slide, is you can search via STAC API that gets converted to a CMR search, finding all indexed NASA data sets. And that search gets returned and translated as a STAC output. So you can search and crawl through NASA's entire collection of imagery through this service. It's pretty neat. And because you're returning STAC, you can use libraries like intake STAC to load, load these files, load what's returned to you. So this example here is loading a measures data set from the NSIDC, and intake provides kind of a, again, sorry, these screenshots are maybe a bit hard to see on people's screens, but it's in a Jupyter, hosted Jupyter Notebook interface, and you're provided with a graphical browser to pan through and look at thumbnails for, in this case, all items belonging to this NASA collection hosted at the National Snow and Ice Data Center. So there are links to more. There's a video summary of this library that came out of the STAC #6 sprint that's linked in the slides. We also have a longer recorded 1-hour webinar talking about some of these tools. And there's also a link to a recent blog post that sort of walks through how this system works in more detail. So I thought I'd just leave links for people to explore later and end there.
Awesome. Yeah, thanks very much, Scott. That's great. Yeah, I think the CMR stack is really a great way to be able to use a lot of these tools with, you know, this whole new archive of data, and which is great. I would add that the STAC index that I mentioned earlier, currently I'm not sure it's completely has completely indexed NASA CMR through STAC yet, but that is coming. One of the things that STAC Index does is give you a STAC browser, and recently STAC CMR has been made browsable, and so that's another way to browse. You can browse through the data, which is pretty neat. In addition to being able to search it. So why don't we do our 1 minute where everybody type in some sort of takeaway or sentence or thought or whatever. We'll start now. Okay, I think it's been about a minute, so everybody hit enter. All right, and if anybody has any questions for Scott, I'm looking here. Lots of comments.
I have one question.
Cool. Yeah, go ahead.
So like if you're running an HPC cluster, like I know this uses intake. Is there any sort of like limitation on bandwidth by using STAC, or is STAC just like a wrapper to make the download easier?
So in this case, this library is just reading STAC to get the URLs to data files and then bringing them in from wherever they live. So for that example I showed with the National Snow and Ice Data Center, you're going directly to the National Snow and Ice Data Center server and actually pulling that. So you're gonna have bandwidth issues depending on the machine you're running from, and also the server where the data is sitting. And so this works best if you're running a Jupyter server in the same place wherever the data is sitting. So if you're running that Jupyter server in the HPC system where you have data and you have an intake and you have a STAC catalog of that data, you can use this system and it'd be very fast.
Thank you.
Yeah, that question comes up. Related questions come up quite a bit about STAC, like oh, does it support some other file, or is it just cloud? And STAC doesn't actually really care what those assets are. They could point to anywhere. You could have a catalog that points to data in some, in some other country, in some other AWS region. James Gallagher has a question. This is a good one. I don't know if there's a driver for OpenDAP. He says, can intake STAC read from OpenDAP servers? Is there a driver for OpenDAP?
Yeah, I don't have much familiarity with working with OpenDAP, but I didn't get into some of the details. Intake is kind of a plugin style library. And so intake STAC just deals with crawling this catalog and then connects to specific drivers for loading endpoints into Xarray. So OpenDAP is one of those where if Xarray is capable of loading the file, then, or loading information from OpenDAP server, you can open it.
Are there examples to integrate STAC with PostGIS? So Joseph, do you mean like the assets are actually like you're using like PostGIS raster or something?
No, not necessarily raster, but if we wanted to use like PostGIS database to do complicated searches between data sets.
Oh, okay. Yes. So yeah, okay. I didn't know if you meant like assets. The assets themselves are in PostGIS. But yes, some of the servers mentioned, so like the Arturo AI is backed by PostGIS. I think Franklin is backed by PostGIS. So some of the servers, that's actually what they're using for their backend. STAC server uses Elasticsearch. I think those are kind of the most common, is like Elasticsearch or PostGIS. Yes, you could certainly, all that data could be in PostGIS for sure. And then you know, that's going to handle your intersection queries for you. All right. Any other questions? Okay. Well, we should probably move on to the legendary Vincent. All right. And he's going to talk about some super cool visualization stuff. This is actually the stuff that like everybody really cares about. You know that, right? Like, because you get to see stuff, and it's not just.
I mean, yeah, but like the metadata and STAC is to me as much as important as the visualization stuff.
It empowers, right? So
yeah. So, but thanks, Matt. Really glad.
Take it away.
Nice intro. Yeah, pretty stressed right now. Thanks. All right, so let me.
Oh, you're muted. Did you mute yourself?
Where?
Yeah.
So you didn't hear anything I said?
Yeah,
before?
not just now. Yeah, you were muted.
But Okay.
We hear you now.
Anyway.
We can hear you now.
Okay, perfect. So you stressed me saying that I was a legend, and now I'm really stressed. All right.
Let's try to throw you off the guide.
Yeah, thanks. All right, let me start then. All right, good. So you can see my screen?
Yes.
Yeah, cool. I can't see my mouse. Okay, so yeah, I'm going to talk about dynamic tiling. And so what I'm saying, dynamic tiling for everyone is just like at Development Seed, and with other companies, we are building tools that help anyone deploy their own services or play with dynamic tiling. So with the different tools and services that we are building. And so, yeah, as I say, as I'm Vincent, work at DevSeed, and I'm also the creator of Remote Pixel, and I'm involved in the CodeGeo Cloud Optimizer GeoTIFF community because, I spend a lot of time working on the subject, and so, yeah. Anyway, so what is dynamic tiling? What does it mean? So when we say dynamic tiling, it's just to compare with static tiling. So when you see a raster, when you display a raster image on the web map, for example, you have two choices now. Either you create the tiles in advance, so you take your raw data, you split your raw data in small chunks, so in tiles. You store those on S3 or on a storage, and then when your clients, the web page is going to request for the raster imagery to load, it will just read the data store on S3 or on the static tiles files. And so in comparison, the dynamic way of doing that is just you keep your file, your input file, you store it as a Cloud Optimizer GeoTIFF, which is a format which is cloud friendly. So it enables range request read, and so basically a cog is just a GeoTIFF, a regular GeoTIFF, but which is made more friendly for the cloud. So you've got a header to the file. Within the header, you'll get the map of each internal tiles. And so basically, libraries like GDAL can just get the header, so the few first kilobytes of the data, and then know where each internal tiles are in terms of byte range. And so when you want to access a specific pixel or the specific range of pixel, you know which tiles and which area to load from the Cloud Optimizer GeoTIFF. And so the dynamic tiling use that. Instead of creating the tiles in advance, we use GDAL to tell our service to read just the part that we want to display on the map directly from the Cloud Optimizer GeoTIFF. And then you don't have to create the tiles in advance. You don't have to store anything. You just keep your raw data. And so that's already like more dynamic than the static way. But you can also like change the way you want your file to appear. You can also change the bands selection. If you have a raster that has a 4-band, for example, with the near infrared band, you can ask the server to display the energy bands instead of the RGB regular true color bands. And so that's why we say it's dynamic. You don't have to store any kind of intermediate files, and you can ask the service or the tiler to do whatever you want with the input data. And so yeah, that's what I'm going to talk today, just how we create tools and how we manage services and how we can help you to do that yourself. And another topic I'll speak about quickly, it's like what happens when you have multiple cogs at the same place, and like, can you create a mosaic? And so can you use dynamic tiling for that? And so I'll talk about that during this presentation too. So one of the biggest tools we just released a couple months ago called Titler is a Python modules that builds with that is built on top of new Python framework to create like a lightweight but fast Python servers and Python services, and so Titler is like the go-to service, the go-to library right now if you want to start using and playing with dynamic tiling, because we put a lot of features in it. So you can, Titler can work easily with Cloud Api Majority. It can also work with STAC. Like if you have a STAC items that has multiple assets that are Cloud Api Majority, Titler can read the STAC items and know how to get to the imagery. And as I just mentioned, we also support mosaics, like virtual mosaics of multiple cogs. And so I encourage you just to go check the repo. We have a documentation website also, which has a lot of info about like the principle of dynamic tilings and how you can set up yourself. But I'll just maybe explain. So yeah, as I say, Titler is just built on top of nice libraries like Rio Tiler, which is a small Python library that we built just to enable like the reading of partial data easily. So it's a high-level library built on top of GDAL and Rasterio that is more user-friendly if you want to read like tiles from any file hosted on the internet. And it's built on top of Fast API, which is a Python web framework, which is really nice, and like it's claimed to be one of the fastest Python framework available, and it is. So, and it really helps for the documentation part. I'll show after. So anyway, the thing which is good with Titler, it's you can just do pip install Titler and get everything installed on your laptop. It also works well remotely on the cloud. Yeah, we have a deployment option for Lambda or ECS or EKS, for example. So it's pretty easy to set up, and it comes with all the features by default. So it's like it can be a bit big, but it has all the features that we thought were necessary. So I just do a live demo, and so I hope you could still see my screen. Yeah, I think yeah, okay. So as I say, just do pip install Titler and then hit start the server. Once the server is running, you'll get to a page. I can't see my okay. And then because of Fast API is a really nice API, it built automatic documentation. So you get documentation for all your endpoints, and you can also play with it directly. So if you have a URL of cogs that I have somewhere here, like you can directly play with that. I'm losing my screens. Okay, and play directly within the open API documentation.
Vincent,
and play with the
Do you need to maybe stop sharing this and share like a different window or something? Is that what you want to do? Did you want to give a demo?
Oh yeah, wait. Oh yeah, I'm sorry. Can I just do that? Okay, sorry.
Yeah,
Thanks.
no problem.
I'm not used to Zoom. Yeah, can you see my screen now and the Titler demo page?
Yeah.
Yeah, cool. So yeah, what I just did was just to start the tile server locally, and then we arrive on the documentation web page. And then you can, so the documentation is built like automatically by a fast API, and you can start playing with it directly. And so I say T-Tiler is built with all the features by default. You support cloud optimizative, but also the STAC, the STAC capabilities, and also the mosaics. And maybe I'll give another demo about like dynamic tiling. So once you deployed, I've got an instance of T-Tiler deployed using AWS Lambda and over API.cogio.xyz. And so if you have a cog URL, just just give the URL to the tiler, and the tiler will be able to display the file, and then you can zoom and like for each tile request because we are using AWS Lambda, it scales really fast. So each tile request is equal to one AWS Lambda function. So it's pretty fast, and you don't have to manage any servers and stuff. So so it scales really well, and it's pretty fast. So as I say, we have example within the T-Tiler repo to how to deploy that in a couple of minutes with a couple of command lines. And so yes, so this is just, I don't own this cloud optimizative. It's a cloud optimizative made by Digital Globe, and which I don't really know where it stores, where it is stored. I just get the URL of the cloud optimizative, and I'm just giving this URL to the service, and then I can just display and play with the data. I can change how the data looks like. I can play with the bands combination, so which is really not useful right now. But if you add a cog with more than 3 bands, or like you can also apply expression, like if you want to, if you have, for example, here I've got the naip imagery stored on AWS. So this is the mosaic part where we've got naip covering the whole US, but it's not one file, it's like thousands of files. And so we have a way using a specification called mosaic JSONs to create a virtual mosaic of those files. And for each tile request, we have a way to just know what are the cloud optimizative that we need to read in order to build the tile that we want to display on the map. And so because naip has more than 3 bands, we can also apply expression on it, and like or change the band combination. So as I mentioned before, and so you can see that's pretty fast. We don't have caching in front of it. We don't own the data. It's stored on a public bucket, and again, everything is done dynamically. So we fetch the original cloud optimized file, and we tell the server to which band we want to use, and how to display them on the map. So yes, so that's, I hope everyone understood why we call that dynamic, is because we have the user just tell the server what it wants to display, and we can apply different operation on the tile directly. And let me just, I haven't shown the STAC part, so I just used again our small instance, and I got a STAC items here. And so this is a STAC items made by Spark Geo, and so a stack can have one STAC items can have multiple assets. So here on the small UI, we see that there are 5 assets. So I can just change the asset I want to visualize in the map, but I can also, like, for example, merge the assets together and apply like different thing on it. So again, that's dynamic. We just started from a stack items and get the address, the URLs for the different assets, and then we can tell the tiler just to fetch, to merge the data together to create the map tiles. And yeah, so that's for the stack part. You just give a stack asset. T-tiler will know what assets it can use. So if you store multiple cloud schema generative in a stack items, T-tiler will know and will understand that it can work with those. And then yeah, you can do pretty much whatever you want. It's pretty yeah, it's user made. Like we made T-tiler to let the more power to give the more power to the user, so they can decide what they really want to do with it. Yeah, I don't know how many times I have left. I usually speak really fast. Another thing maybe I'm going to show is just because it's dynamic. Once you store a cog on AWS, like, because it's dynamic, you can do whatever you want with the data itself. And so this is just a little experiment I did last week. I've got a cog displayed here. It's LULC results, and so it's a class data. And like, so on this part, I'm displaying the tiles are as raster tiles, and on the other part, it's not a raster anymore. It's the vector. So on each tile request, I'm creating a vector tiles of the region I'm reading, and then I'm giving the vector back to the web interface. So on the right side, just the comparison, we see the raster imagery, and on the left side is just the raster imagery that we converted to a vector tiles, and that gives us like more features. Like we can click. Because it's a vector, we have the information directly in the front end, in the client, and like we can click on the vector and select and do whatever we want. And so this is just a little experiment just to show how dynamic it can be. And like once you have your cog stored somewhere, you can do a lot of operation live when you are loading it and displaying on the web client. So yeah, that's just another example to show how dynamic it can be, and how like I just store one file somewhere on S3, and then we can have a lot of opportunities, and like we can do a lot of things once we have one cog stored somewhere. And you could like, yeah, apply some operation to do some processing on a stack of cogs directly using some features that T-tilers offer. And yeah, that's maybe, yeah, everything I wanted to show for the demo. And yeah, maybe I can go back there and talk about optimization, customization. So T-tiler is a Python module. So you can import T-tiler on your own API and just deploy different endpoints. You can create lightweight, like you can remove most of the default endpoints that T-tiler create. And so we try to build something which is user-friendly, which use the latest improvement of Python frameworks, and with using Fast API. But we also try to build T-tiler in the way it's really customizable, and that the user can do whatever they want. And so I encourage anyone just to go on the repo, look at the documentation, and try themselves just to try locally or to deploy on their infrastructure. And that's it. I don't know how much time I had, but
yeah, that's I don't know, you probably went over it. It's all right. That was great. Thanks. I know that we're planning on using T-Tyler ourselves. It's really great. I also like the fast API. Rob had mentioned that earlier, yeah, I think that's the way to go. I've got a question. I'm looking to see if there's any other questions. We only have a few minutes left, so I would like everybody to go ahead and take a minute and type in something. But while you do that, I'm going to ask my question. So Vincent, with the Sentinel-2 data, we have tiles, internal tiles that are 1024 by 1024. You know my question. And with the recent Landsat Collection 2 data, their tiles are 256 by 256, right? Which one's better? What do we do?
So we had this discussion on Twitter a couple of days ago, and it's hard to choose one configuration for your cloud API measurative. So for anyone else, the cloud API measurative is a regular geotiff, which is tiled internally, and the tile dimension, you can choose the tile dimension, and some choose big tiles, some others choose small tiles. And it depends on the use case of your user. Like big tiles, every time you are going to try to load the data, you are going to load a lot of data. So like for dynamic tiling, it will you transfer a lot of data from maybe reading that maybe you only need 25% of the data that you transferred. And so, but when you use small tiles, you end up doing more GET requests. So it's hard to find the trade-off between getting a lot of data or getting a lot of requests. And so I was part of the discussion when we choose to turn on the tile size on the Landsat data, and it's really hard. But if you like, my use case myself is dynamic tiling, and so small tiles are often better. But like, it really depends on the use case. And when we talked about the Landsat data, we didn't talk about dynamic tiling. I just thought that if the user wants to read 1 pixel, for example, of the data, like smaller tiles are easier. If you want to work at scale and you don't care about how the image are displayed, but want to, like, if you just want to read like a 200 pixel window of the data, it will be easier to work with small tile dimensions. It's a really hard it's a really hard question, Matt. And
yeah, no, I know, because there is no one answer, and also I think it's the use case. Like if you're within region, right? Like if you're doing dynamic tiling from another region, that's a whole different thing than if you're tiling within the region, because that data transfer is really quick. And it's usually the overhead that's most of the time, right? So,
yeah, good point too. I'm ambivalent on that. Sometimes I use big tiles, sometimes I use small tiles. It's really hard.
Yeah. So maybe some more testing. It would be good to see some more benchmarks too for different use cases as well. So there's another couple questions here. So Scott asks, what if a float or float 64 band is sent to T-Tyler? Does it need to be integer? Can it handle floats?
Yeah, it can handle floats. And as I said, it's dynamic. So if you want to apply different rescaling factors, you can. I didn't demo anything, but like if you have a data that is not int 8 or byte, T-Tyler will ask you by default to rescale the values from the min and max of the file. and but it's user centric. So you have to give the info to T-Tiler. T-Tiler will make some decision for you, but usually it's on you to know what kind of data you are loading. But you have the ability to give the information about how you want to display and what kind of risk scaling factor, risk scaling value you want to use.
Okay, and no data can be either a no data value or an alpha mask?
Yeah, yeah, and you can also overwrite the no data value if there is no data value in your code, which is a bad decision. You should always put no data or alpha band or mask in your code.
Yeah. All right. One question about STAC here. Ted, hi Ted. Does STAC support connections to more detailed metadata for interoperability and reuse? Yes. And so the focus of STAC, right, is on having it be simple and extensible. And so for the card4L extensions that we're talking about, one of the things that you can do is actually link to the other file, right? Like you could link to other metadata files. I really like that approach rather than trying to cram more stuff into STAC. Is because STAC makes people should make judicious use of links in STAC records. So link to scientific papers, link to documentation, link to other metadata files. Those could be an asset itself or a link. So because a lot of the more detailed metadata really, it doesn't contain information that's really useful for search and discovery. It's more about usage, and you don't want to really bloat that record because it's nice to have it be somewhat human readable. All right, well, we're out of time. This has been a great session. Thanks for all the speakers. This has really been great. We have a whole lot of great feedback here and thoughts as well. So thank you. Enjoy the rest of the day and the conference.